okay? But we already talked about some of this, I think. We're not going to talk, well, we'll talk a little bit about the point that light is made up of is electromagnetic radiation. Remember we talked about that when we talked about waves, okay, a couple of chapters ago. And it's made up of electromagnetic energy. I'm going to skip all that. Reflection and refraction. Did we talk about that? Reflection? Didn't we talk about that last time? Or no, am I wrong? We do reflection and refraction? No? Well, wait a minute, let me go back to 14, and I don't want to cover something that's not going to be on the speed of light. Oh yeah, we need to do that. We'll start with refraction. Reflection will have, well actually reflection and refraction, we'll do a lab on that. But the law of reflection just says that the angle of incidence, meaning the angle at which the light ray comes in and strikes the surface, is the same as the angle of reflection that it is reflected from the surface. Now in this case it's a flat surface, but this is always true. When you draw a perpendicular to that surface, these angles will always be the same. Right? There's no difference. It doesn't even matter if the mirror is curved or not. They'll always be the same. The reason you see yourself in a mirror, remember you're seeing a virtual image. You're not on the other side of that mirror, but it looks like you are, right? It looks like you're over there, but what's really happening is when you look at your feet, what you're seeing is actually the light coming from your feet. Remember, the light has to come from something in order for you to see it. If the light doesn't come from it into your eyes, you ain't going to see it, okay? It's got to come through. So in this case, the light from your feet, they go up and they hit the mirror, and according to the law of reflection, then they go right into your eyes, and that's how you can see your feet. But your eyes get fooled by that. Our eyes always think, it tells our brain that everything is in a straight line. So we think we're actually over here on the other side, but we're not. Okay, we're being fooled by the mirror. The same is true about the top of your head. You look at the top of your head in the mirror, what's actually happening is the light's coming from the top of your head, hitting the mirror, and then coming back into your eyes. Okay? But it looks to you, when your brain, tries to straighten it out, it looks to you like you're over there. Okay? So when you're looking at a plane mirror like this, you're going to be the same distance from the mirror. You're going to, in the virtual image as you are in reality, you're going to be the same height, but there is a right to left reversal. Okay, now when you bend the mirror, when you bend that mirror, you can play tricks with that, and we won't go into that because I'm not going to ask you anything about that. But for example, the convex mirror, this is the kind of mirror that you have on the passenger side of your car, right? And it's bent, or I shouldn't say bent, but it's curved outward like this. And when you look at it, the image that you see from the outside is going to be a virtual image. It looks like it's in the mirror, but because the mirror is curved, the distances are wrong, right? And doesn't it say that on the mirror? Right? Doesn't it always say something like objects are closer than they appear, right? It's because you're seeing a smaller version of it. Like in this case, I just tried to show it. If your face, you were looking in there, you see a smaller version of your face. But I just want you to realize that's what's going on with that passenger side mirror. So the distances are off, all right? But it gives you a much wider field of view, okay, when you look at that. Or when you go in stores, if they want to watch and make sure you're not going to steal something, off one of these shelves, right? They have these mirrors up in by the ceiling where they can look and they can see what you're doing as you're walking along the different aisles. But again, that's a convex mirror. So you look smaller to them, but they can see where you are and what you're doing. Okay? So, the difference between spectral and diffuse reflection, just want you to realize that diffuse reflection is what almost all reflection is. For example, if, let me try and think of an example here. If I can think of, try and think of an example that would give me the two different options. For example, light from, well, I guess I should just say light from any object is going to be diffusely reflected. Now, I want you to realize that everywhere a light ray, if they all come in, all the rays come in parallel, everywhere that they strike, the law of reflection applies, okay? The angle they come in at and hit the surface at that point, that's the angle that they go out at. But the problem is, this surface is irregular. So what's happening is these light rays, while they all come in uniformly, they go out at different angles. This is why, for example, I can see, for example, I can see Peter from anywhere in the room, right? No matter where I walk in this room, I can see him, right? You say, yeah, we know that. But that's because the light that's hitting him is being diffusely reflected everywhere. So no matter where I stand, I can see some light coming from him. On the other hand, if this was a mirror on the wall here, you guys realize that in order for me to see him in that mirror, because now all the light rays are being reflected perfectly, all right, now what happens is that, that I will, if I walk over here, I won't see him anymore. I'll see something else, further away, right? Because the mirror is only reflecting that image perfectly, right, from that one place. I just want you to realize this diffuse reflection is probably 99.999999 of all the light reflection that we have in our world, right? And that's why we can see things from really any perspective. It's because of the light rays being diffusely reflected. You okay with the difference between those two? If I ask that as a question, you're okay with that? All right. I haven't tested it yet, but that's... No, we don't know sound obeys it too. Now, boundary. When light goes from one medium to another, and this really applies for all electromagnetic energy, right? We're just talking about light for right now. When light goes from a less dense medium like air into a more dense medium like water, okay, what happens is the angle of the light ray changes. And in the more dense medium, it gets closer to that perpendicular, it's called the normal, to the surface. And when we do this lab, you guys will be actually measuring this. You'll be seeing this and measuring it. So that's the, that's what happens. And the opposite happens when the light's going from a more dense, more optically dense to a less optically dense. The light ray gets bent away from that normal, so you have a bigger angle on the air. In other words, you always have a larger angle on the less dense side than you do in the more dense. I don't know if I have a... No, I didn't. Give me an example. I digress. When I was about 10 years old, my boyfriends and I, we would go hunting, and we didn't have guns at that. My parents wouldn't let us have guns. Living in New Jersey, it's a serious. Guns are serious things back then. Use them to kill people, and mafia and all that. But in any case, we had bow and arrows. Okay, so when I was around 10 years old, we used to go hunting. We were all excited. We made our own arrows, and we had like a little gang, like there were 3 or 4 of us, 5 of us maybe, that hung out together. One day, one of the boys said, hey, that big lake, it's like a couple of miles away. He says, they've got some big fat carp in that lake. Let's go, we'll tie some string to our arrows so we can get it back. Let's see who can shoot the most carp, say in an hour. Yeah, we all got excited, right? So we get some string and we get our arrows all ready with string on them. We get on our bicycles and we go up to this lake. All right, now we got to the lake. And we spread out, 50 or 100 yards apart, something. And we're walking along. And I remember I was walking along, and I saw, it must have been about, maybe 5 yards out or something, a big carp in the water, probably this deep, but just swimming by, So, I got all excited, right? Took my bow, aimed, shot, and I missed. Okay, so I pulled the arrow back in. I walked around the edge of the water a little further. I saw another carp came by. So I took aim, and I shot, and I missed. And I said, wait a minute. I can hit a rabbit at 40 yards. I can't hit this fish right here. And I was just very confused. And my buddy that had set this up, he's laughing at me. He says, you can't hit him, can you? I said, no. He says, there's a trick. I said, a trick? What do you mean? He says, you'll never hit them if you aim at them. He says, you have to aim under the fish. I said, what? He said, you will never hit it if you shoot right at it. You have to. So I said, okay, I'll give it a try. So I walked and I saw another car come by. So I aimed at the fish and then I aimed under its belly and shot. Bingo, got my fish. Right? Now that's a little personal story, but that's my first introduction to refraction. I had no idea what it was at that time. I just knew it was a trick that you had to know in order to have that happen. But what was happening is your eye is looking like this, all right? But the fish is actually down here. So your eye thinks the fish is up here, but it ain't. So when you shoot up here, when you shoot directly at the fish, that arrow is going to go right over its back. All right? Because of this refraction. The fish is down here, but because the light from the fish gets bent in that direction, it gets its direction changed. Now, you think it's your eye, just like we talked about with the mirror and your image on the other side, our eyes get fooled. Our eyes are always making straight lines everywhere. And that doesn't work when there's refraction, because the light changes its direction a little bit. So, anyhow, that's refraction. Okay, the light, if that happens because the light changes its speed, it slows down when it gets in a more dense medium, and when it slows down, its direction also changes. But, let's see, we won't do any of that. This was an example of when I used to be able to show video cassettes here. I could show about this, but I just want to point out to you that another effect of here, for example, another effect of refraction is when you look in the water and you see something underwater, it actually looks to be closer than it actually is. A little bit closer. You're fooled. Right? You have to be careful. But it's because of the light getting bent in its direction when it comes off. Birds like osprey and eagles, they have to learn when they go into the water and they see a fish that's maybe a foot or so under the water, and they're going to grab that fish. They have to learn to do like me with the bow and arrow. They have to learn to grab, first of all, behind the fish, and then down deeper than the fish looks like. So they have to learn that. Right? That's one thing that these birds have to learn by experience, or go hungry. So, but anyhow, that's refraction. Do we have any more on refraction? Well, no, just why does light bend? It just bends because the speed changes, and that changes its wavelength. The speed of light depends on the medium. The frequency doesn't change. Remember, this was the equation we had in that last chapter. The speed will change, the frequency stays the same. So if the speed goes up or down, the wavelength is going to go up or down. And this, this fraction is called the index of refraction. And what it is, it's how fast the light is going in outer space versus how fast it's going in some other medium. It could be air, it could be, because air is more dense than outer space, where there's nothing. Or maybe water, it could be oil, it could be glass. Okay, when we do it in the lab, it will be glass. All right, the speed of light is going to be slower than it is out in a vacuum, so this number will always be greater than 1. But that's how you calculate the index of refraction. I think you have one problem with that I asked you about that. And this was an example how fast is light traveling when it goes through diamond. Where you look up the diamond, its index of refraction is very high, actually, 2.42. So you say, well, if the index of refraction is 2.42 and the speed of light in a vacuum is always 3 times 10 to the 6, you solve for the speed and you can figure out what the speed is. But anyway, that's the formula you would use for that. And now, lenses. Lenses use refraction. That's what this is, right? That's what these are, or contact lenses. They're using refraction to change the direction of the light when it goes into your eyes. And it does that by, well, we're going to just talk about the lenses first of all, but then we'll talk about the eye in particular. But you can either find the image, all right, when you're given if you're given a problem where there's a lens in it, and that lens, you'll draw this this reference line, you put the lens in there, every lens will have a focal length. All right, and the focal length you can get by let me see. For example, well here, the focal length of this, oh no, I have to get, I didn't bring one with me. I was going to bring a magnifying glass with me. But I was just going to show you how you get the focal length. Well, I guess probably a lot of you, especially the boys in here, didn't you used to use a magnifying glass to burn ants and things, right? You know, what you're doing is you are concentrating the light from the sun, the parallel rays coming in. You're concentrating them at that focal point. Okay, that's where they go. Parallel rays go right to the focal point. So what happens is you're condensing all that light into one spot, which of course gets very hot when you do that. So you can find the image, knowing where the focal length is, you can find the image on either side of a lens. And there's two ways to do this. You can do it graphically by just sketching here roughly, but reasonably, where the focal lengths are. I have that in red here. And then you have an object there. At the top of the object, any light ray that goes parallel into the lens will get refracted through the focal point, just like you do when you're burning those ants. All right, it comes through. And any light ray from that object that happens to go through the focal point on this side comes out parallel. They're just the opposite of each other. And where those two lines intersect, that's where the image is. That's the top of the image. So in this case, it's going to be upside down, and it looks like it's going to be a little bit bigger the way I've drawn it there. Now you can figure this out from with math, exactly where it is, by saying this. If you know the formula is 1 over the focal length equals 1 over the distance that the object is from the lens, plus 1 over the distance that the image is. So there are 3 variables here, 3 of them. The focal length, the object distance, and the image distance. And when you plug the numbers in, like in this case, I chose from up here, the object being 20 centimeters from the lens, and the lens having a focal length of 10. All right, where is the image? You just plug it into this formula. So it'll be 1 over 10 equals 1 over 20 plus 1 over whatever that image distance is, and you solve for that. And I just move this over to the other side, so it's a minus. And then you guys just do the algebra, or the math, I should say, the way you want to, the way it's most comfortable for you. You may want to use that formula when there's only 2 things like this on the other side. Remember the formula, that we had for parallel resistors? If there were just 2 of them, that's the same formula you would have here. In this case, it would be, the numerator would be 10 times 20, and on the bottom would be 10 plus 20, just like we did with the resistors, and that would equal the image distance, and it will come out to be 20. But anyhow, however you guys want to do that math, it's, whatever is you're more comfortable with is fine with me. Okay, so that's how we do that. And I just wanted to point out to you, what is a mirage? A mirage is the refraction of light from the atmosphere. What happens is on a hot day, you have warmer air underneath the cooler air. It hasn't risen yet, so it's just right above like the asphalt, or in the desert, on the hot sand. It's going to, the light is just, it's keeping the air just above it very hot. What happens when you do that is the light from, say, a car is approaching, you're on the road. Well, you guys know the light that strikes the car and goes into your eyes, you see the car. Okay, but ordinarily, what happens is the light that, if there wasn't that layer of hot air here, what would happen is the light from the car that hits the road would reflect from the road, but it wouldn't go into your eyes. It would go somewhere else and hit you lower and you wouldn't see it. But because of refraction here, when you have that little hot layer of air, it changes the direction of the light. And you'll see this when those of you that are in the lab, you'll see this when we do the lab, how it just shifts the direction of the light over a little bit. So what happens is when you're looking at that, you are still seeing the car, you're just seeing it upside down here. When you're looking out at the road and it looks like there's water on the road ahead, all right, what is that water? What's actually making up that water? What do you actually see when you look at that? You think of what it might be? It's a sky. It's a sky. You might notice that sometime now when you're going, you'll see water up there, and then there might be a tree something off to the side as you're driving, and you'll see the tree upside down, you know, in the water. That's what you're actually seeing is the sky and the clouds, or what's up there doing the same thing to you. I just want to point out that because of refraction, when we see the sun just dropping right down to the horizon, you know, over the Gulf, you know, for example, it's actually already set. The light is just being bent so that it looks like it's still above the Gulf a little bit, but that's just due to refraction. But anyway, these are small points. I'm just trying to broaden this discussion out a little bit. I'm not going to ask you anything about a rainbow, but this is that occurs because of tiny droplets of water in the air that are refracting the light and splitting it up into its different colors. I think I may have told you, Isaac Newton was the first one to show that a light ray is made of, a white light is made up of different colors. Can I tell you that? When he was about 20 years old, he was going through, I guess today what you would call a flea market, but some kind of a fair, and there are always these people selling different gimmicks, and one of them is if you have a type of glass, particular kind of glass, and you have it at a particular angle, a particular index of refraction, and you cut it at a particular angle, when you shine light into it, the light will go in and get reflected inside, and reflected inside, just like in a raindrop, and then come back out and get refracted again as it comes out, and it splits the light up into different colors. And everybody thought that that was magic at the time, that that particular glass, you know, was doing magic. But Isaac Newton, he bought two of those prisms and he took them home. And when he was home, he fashioned something like a piece of cardboard or a piece of wood with a little hole in it in his window so that a beam of light from the sun came straight in. And then what he did is he shined that beam of light into one of those prisms. And of course, then it broke into its different colors. But what he did that was really unusual, as observant of him, is he took the second one and put it next to the first one, and he got those colors to go in and come out white on the other side. So he was the first one to figure out that white light was made up of all those colors. Now, of course, you can imagine back in those days, you know, people just said, well, you must be nuts. Anybody can see it's white. It doesn't have any color. We were trying to tell him, no, it's white because it has all the colors in it. You know, but anyway, he's the first one to have done that. He's the first one that he called it a spectrum. And he gave it that name, a Latin name for the breaking up into different colors. Of course, he didn't know they were wavelengths. He just knew they were different colors. We had to figure that out here. Well, this is an important one. This is total internal reflection. If you take a flashlight and set it on the bottom of the pool so it's shining up at night, all right, if you don't have too much light reflected from the sides of the pool, what will happen, you'll be able to see when you stand back and look at the pool, you'll just see a big circle of light on the pool. That's it. You won't see, outside that circle, there won't be any light. The water will be dark. And that's because the light, when it comes, remember like we had in the earlier drawing, when the light goes from the more dense to the less dense, it gets bent away from that vertical, that normal. So what happens is you're going to reach an angle here where the light is now, it can't get out because the angle will be 90 degrees or greater. It can't get out. What happens is that all the light gets reflected back into the pool. This is called total internal reflection. This is what happens with Christmas time when they have those fiber optics with the different colors in them, the lights going through the plastic tubes. What's happening there is the light waves that are going through that plastic or that glass, they can't get out because the angle is too great here. They can't make it out. So they just bounce around inside until they finally find an opening. So thank you. Until they finally get an opening and they come out. This is why cable TV is so important, right? When they lay these cables, they can put millions of different signals through there, carrier signals that are all those little different frequencies so that they don't interfere with each other, and then they unscramble them on the other end. So you get your Netflix or Comcast has. You're getting all these, but the reason is when they send that signal from wherever they're sourcing it, it's trapped inside that cable and can't get out until they let it come out, like at your house, okay, and then unscramble it. But that's all because of what's called total internal reflection. Okay, that's it. Now, let's do the other one. And let's see, that would be, there's this, and radioactivity. Here we go. Let's see, but I didn't talk about atomic physics. Well, maybe we just, you guys do the homework on that, and that'll be good enough, I think, on the atomic physics part. That's chapter 17. I don't think I have it in this list, but we'll see. You've probably been to the Edison home here, or when you have company or something. You've been, I haven't been there since Hurricane Charlie, so it's, but before Hurricane Charlie, they had a lot of different plants from around the world that were plants that secreted some kind of sap, okay? Back in those old days, the rich people that traveled around the world, when they would go to different countries and they would find a tree of some kind that had sap coming out of it, they would get seeds from that tree and send it to Edison because he wanted to see if he could refine something out of that sap for tires, okay? So they would send him these seeds and then he would plant them down here. He couldn't plant them in New Jersey because they die in the winter. But he would plant them down here. And they used to have a lot of different kinds of bushes and trees that were from other parts of the world. But they were put there by Edison because of the seeds he got from his friends. And of course, then it went on to, he'd use that to try and make a better tire, a better rubber for the tire. But in any case, the reason I bring that up is, well, Edison would look at these seeds and try to find something that made a better rubber for the tires. In those days, there was a laboratory back here in the late 1800s in Paris that was a place where people would send any kind of new rock that they found. If they were a geologist of some kind and they found a new rock and they couldn't figure out what it was, they would send it to the University of Paris. And in there was a lab there run by a guy named Henry Becquerel. Probably it's in your book, but not here. But in any case, he had Marie Curie and her husband Pierre working in that lab, and their job was to take that rock and then dissolve parts of it, take it apart, and figure out what the different chemicals were, the compounds that made up that particular stone. So, like Edison in those days, he was just looking at the different rocks. Well, one day he got some rocks in, and he threw them in a drawer. Closed the drawer and figured I'll get to them later. And a few days later, he wanted to take a picture of something. And in those days, we didn't have movie film or digital cameras. Back in those days, they took pictures on glass plates that had a light-sensitive coating on one side. And so they were kept out of the light, obviously, in the drawer. What he would do is, what he did then is he took some of the plates out to take a picture of something, and when he took the picture, he found a big splotch of light on the picture. And he said, what did this come from? And then he realized it was because the rocks that he had, the stones, that he had in this other drawer, were emitting something, some kind of energy that was fogging up the glass. And so what he did is he said to Marie and Pierre, you guys figure out what's going on here, and they did. She gave it the name radioactivity, and we call it nuclear radiation today, but she gave it the name radioactivity, and the radioactivity, the rate at which the radiation comes out is constant, but that's because each time radiation is emitted, it's emitted by an atom that only does it once, and then it's over. But there are so many atoms in any little tiny sample that we have that we always have something coming out for many, many years. It will just continue to come out. So that's why the radiation rate is constant, but once each atom emits it, it does it spontaneously. We can't control it. We can't heat the rock up and have it emit more radiation or put it under high pressure. No, none of that. We can't control it in any way. It just happens naturally. Mother Nature has her own, her own process for this, and she's not letting us mess with it. Now, this radiation comes from the nucleus. And so the electrons that are orbiting the nucleus, all right, they aren't involved in this. It's only the nucleus that's involved. And Marie Curie came up with 3 kinds of radiation. And since they didn't know what they were, they just knew there were 3 kinds. They called them ABC. Like today, I guess you would say X, Y, Z, right? But she called them ABC, but ABC in Greek is alpha, beta, gamma. Okay, so that's where these names came from. The alpha are the heaviest particles. They're actually a helium nucleus. They have a positive charge, okay? And an example would be here, uranium decays by emitting this helium nucleus, this alpha particle, and it changes into something else. Once you remove any protons from the nucleus, you change the element. It's now a new element. So it's called transmutation, but it now changed into another element. But this is something that's, that's going on naturally all the time. But that was the first particle. The second one came about, as it turns out, it was an electron that was being spit out by the nucleus. Not from the electrons that are on the outside. Electrons that are in the nucleus. You say, well, wait a minute, the nucleus is positive. Where do you get an electron in the nucleus? Well, it turns out we learned that a neutron that has no charge that's in the nucleus, it's actually made up of a proton and an electron. And so what happens is when you get this beta particle emitted, this electron gets spit out. When it does, it adds 1 proton to the nucleus. So in this case, carbon-14, which probably you guys have heard of that. We use that in medicine a lot. Carbon-14, when it decays by beta emission, it spits out that electron, it changes into nitrogen. So that's just what happens. But it happens because, remember at the time that Marie Curie figured this out, we hadn't figured out yet what the atom was like. All right, this was much earlier than that. So this was a lot of very careful work that was done by her, so we could fit all this together later on. Well, this isn't chemistry, but I was going to tell you one thing. One thing I was going to tell you, like these alpha particles, we don't have a periodic table in here, do we? No. Well, in the periodic table, the columns in the periodic table are all elements that chemically behave exactly the same. They start with the lighter ones, and they get heavier and heavier, bigger atoms as you go down. But chemically, they behave exactly the same. Hard to tell them apart, chemically. All right. One of the things that we did is back in the 1940s, and I guess up to around 1950, we used to do atomic weapon testing in the desert out in the Southwest. We had, a huge area, these big areas of no man's land, fenced off, nobody could get in, and we would blow up small atomic bombs in there just to see, how we can make them more effective. Okay, which is, that's research, right? That's what they do. And so people say, well, wait a minute, what about the radiation? Well, don't worry. All right, we got all this area, and any dust that's there, this little cloud goes up, but it's this small cloud, goes up, and when it comes back down, all the dust is right here. So we measure it, we know how much radiation there. Don't worry about it. Okay, so we did this testing for a number of years. Then around, I should look up these dates, but around 1950, I know it was after World War II, and around 1950, pediatricians in New York State found that in one area, upper New York State, large area, children were coming down with leukemia. And the doctors were saying, something's really crazy here. We have more kids with leukemia here than anywhere in the country. What's going on here? And so they began to investigate what was causing it. And what they found out was one of the radioactive elements from the explosion was a radioactive strontium, strontium-90. It was a radioactive element. It went up in the air. It was very light. And what happened was the jet stream picked that strontium up and blew it across the United States and dropped it in New York.
Wow.
So it landed on the grass in New York. Okay. Now, I told you when you're in the column on that periodic table, everything behaves the same. Calcium is here, strontium is right underneath it. Chemically, they're identical. All right? So, it fell on the grass. What eats the grass in New York State? Cows, right? And what do the cows make? Milk, right? What kids drink, right? There you go. What was happening was the cows would eat the radiation, their strontium. It would go into their body, and their body thinks, hey man, this is calcium. And they put it in the milk, as well as the rest of the cow, of course, in its bones. But then the milk gets, nobody knows any different. They process the milk, sell it to people. All right, and kids are drinking this milk. It has strontium in it, which, of course, it has calcium as well, but it has a lot of strontium in it. And these children now have strontium in their body, and when it decays like this, it causes cancer. Okay, so that was when they realized that they could never again test atomic weapons in the air. That's why when you see, and I don't care if it's North Korea or anywhere, people are always testing underground because they want to track all those particles. That's a sad story, but that's a true story. That's give you a little chemistry there too, but that's what fooled people for a long time. You really needed a Sherlock Holmes to figure that out, how all that fit together. But that's what was doing it. But it was this kind of a deal. But I just wanted you to realize on that periodic table, everything that's in a column is chemically indistinguishable from everything above or below it. Okay? They behave exactly the same. So I know a little bird walked there, but I wanted to give you guys a little, just a little more insight into this. Carbon-14. I've done experiments with that, but I won't keep you here for that. Burn bandage, developing a burn bandage, the FDA wanted to know where one of the constituents of that bandage went when it got into your extracellular fluid, where to go. So I had to work with some rats and figure that out. But anyway, carbon-14 is a beta emitter, and lastly we have gamma, which is gamma radiation is just radiation, no particles, just radiation. I just have an example here of alpha particles. Now remember, any of these are dangerous if they're in your body, if they're next to a cell. All right, they're going to damage the cell. But in terms of being in the air, outside, the alpha can be stopped by a sheet of paper, the beta by a little thicker, a little piece of wood or some aluminum foil. That will stop the electrons. But the gamma, you need a lot of lead or concrete, and those of you that are in the CVT program know about that. You have to wear protective gown when you're working with gamma radiation. Okay, but, so they'll all damage cells. And this was just to show you that, I just wanted to point out to you that as the number of neutrons and the number of protons in the nucleus are the same up to a point of about 20 of each. And when you get beyond that, instead of that staying equal, you now have more neutrons and mixed in with the proton. And this is why they think that decay takes place, because there's so much energy required to hold these bigger elements out here, to hold these bigger ones together. Remember, anything that's 84 protons or larger, it's radioactive, period. All right, everything. But it's because these guys, they're held to, the nucleus is held together, but only, let's just say, barely held together. And at some point, it has to get rid of a piece, and then off comes that alpha particle, for example, because it has to release it. It can't hold it. That's why they believe that that's happening. And no, well, you don't have to know that. But anyway, I just wanted you to realize that's what's happening. The nuclear force. Right, didn't we talk about the nuclear force in the lab a little bit when we had the film? No? It was the film. It was in the film, so I mean, that nuclear force is what he's talking about. The weak and the strong forces are the ones holding the nucleus together. But once you get above 84, they can't hold them together perfectly, and that's why we have that breakdown where some split away, the alpha particles split away. Okay, half-life. The half-life of a radioactive element whenever you want to figure the half-life, you're always going to start with 100%. Now, maybe, well, like in this case, if you have the radioactive iodine, iodine-131 has a half-life of 8 days if you have it on the shelf. How much radioactivity is left after 32 days? Well, what you do is you make a little chart like this that says, there's actually a math formula for this, but I figured we'd stay away from that. Because I think this is easier to understand. Certainly it's easier for me to understand. The thing is, whatever you start with, I don't care what it is. I just said 100%, but it might be, they might tell you, well, you have 20 grams of it. Okay, if you start with 20 grams, put 20 grams in. The thing is, after one half-life, that's when half of all the radioactivity is gone. It has been put out. Okay, so you only have half of that amount of radioactivity left. So that means if you start with 100%, you're going, after one half-life of 8 days, you're going to have 50%. Okay? Now, when you go another 8 days, how much do you have? What do you think?
25.
It's going to be half again, 25, right? Not 0. I don't want you to think it goes down to 50%, then 0 goes to 50%. Now it starts all over. Another 8 days goes by, it's half of this number. So it'll be half of 50 is 25. All right? After another half-life, it's going to be half of 25 or 12 and a half, and so forth. That's how you work that table down. If you were told it was 10 grams or 20 grams, as I said before, then you'd say, okay, I got 20 here, now I have 10, now I have 5, now I have 2.5, now I have, and so 1 and 3/4, 1.3 or whatever. Okay, you guys see how you figure that half-life? If I give you a problem like that on a test, you can do that? That's how the half-life works. Fission and fusion, I just wanted you to know, fission is what happens when we, I think those of you in the lab that saw the connections video, that's what happens when you bombard a nucleus with neutrons, a big nucleus, like a uranium or plutonium, a big fat boy. When you bombard that with neutrons, the neutrons, if any of them should hit that nucleus, they get absorbed. Now that nuclear force can't hold it anymore, so boom, it splits it apart and releases a lot of energy. That's how fission works. But I'm not going to give you any questions about that. I just wanted you to know technically, give you an idea of how that works. When you look at how a nuclear power plant works, first of all, I want you to know that a nuclear power plant doesn't have anywhere near the amount of radioactivity to be a bomb. So you can't have an atomic blast. There's only a few percent of radioactive material in there. It can't happen. But there's still an awful lot in terms of making electricity. So, but I won't go into that. I'm going to skip that part. Fusion is the opposite of fission. It means where you're combining things to make, a larger atoms, two smaller ones. And in the sun, this happens naturally. In the sun, what we have is that the hydrogen, 4 hydrogen atoms get together and they make a helium atom. And this reaction, when they go together and they fuse together, that releases a tremendous amount of energy. In fact, it was Einstein's equation, E equals mc squared, that figured that out for us. It said the amount of energy released is going to be the mass multiplied by the speed of light squared. That's it. But that's how we can figure out how long the sun is going to last. We know it's about halfway through its life. But don't worry, we've still got about 5 billion years to go. So don't have to worry yet. Not a problem. All right, now, ionizing radiation. This is, we use this term to say that the radiation, when it strikes a molecule, what it does is it will knock off electrons, from those atoms, and it will have an effect that caused that atom to then react in a different way. You only have to change an atom a little bit, and it doesn't work anymore. For example, they have, you can get heavy water, they call it. It's simply a water molecule that just has one extra neutron in it. That's all. You know what? If you water your plants with it, they will die. right? They die because that one extra neutron makes that water unable for the cells to replicate, so you're done with that. So I just want to point out to you, sometimes a very small change, on a molecular level can make a big change in reality. So that's what goes on here with radiation. And in the room I used to teach this class, and I remember one day I was going to show a Geiger counter, and I went to the back of the room and got the Geiger counter, and as I was walking to the front, it was just going blink, 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 background radiation. And as I walked by one person, right? It was a girl. As I walked by, it went. I said, "What? What's going on here?" And she just said, "Oh, I'm sorry. I had a procedure today where they injected me with the radioactive material." So, okay. So I want you guys to know when they do that, you're going to have that radiation in you for a while. But we'll talk about how we can calculate how long, which of course we do in the office anyway. I just wanted you to realize one of the things I did in the last job I had in industry was to make these little seeds, these radioactive seeds. They're actually a little tiny titanium can, inside of which is some radioactive material. The can is sealed all up, and it's very body compatible, tissue compatible. And what happens is, though, you put that little can inside of a tumor, and what happens is it kills all the cells immediately around it, which your body then sloughs off. And so the tumor gets smaller and over time disappears. And of course, the radiation oncologist, and in this case where I was working, the urologist together, they figure out exactly how much radiation to put in so that by the time you go from here to there, all the radiation is gone. Okay, so they figure all that out ahead of time. But this is, if you hear about the treatment of tumors or a particular prostate cancer, they're putting these little seeds in. That's what they're doing. They're putting those seeds in. They don't, but in that case, they don't put one in. If it's a prostate, they end up putting, I think we would put in something like 50 or 60 of them, spaced all throughout the prostate. They're really tiny, but they would spread them all around, and they've already figured out with the software how that's going to shrink that prostate down to nothing. So you just have a bunch of little tin cans in there, little titanium cans. But anyhow, I just wanted to show you guys a practical aspect of this. This was an example. I'd like you to, and again, I have the mathematical way of doing it over here if you want, but if in this case the half-life has a half-life of 2 days, and you have 4 grams of it on Monday, how much will you still have on Tuesday of the next week? Well, you got to figure out, in that case, here are the days. It's 2 days. You have 2 days for one half-life. So that's Monday, Wednesday, Friday, Sunday, Tuesday. But can you see this is the same structure that we had before with the percents? So all you need to do, once you set that up, where each space here is a half-life, you say, okay, if I started with 100%, now I'm down to 6.25% down here. Or if I said up there it's 4 grams, 4, 2, 1, half, quarter. Okay, so you guys can do that? You okay with that? I just want to show you another problem. You'll have something, a problem or two in the book like that too. Now, I think this is the last thing. When you have a radioisotope in your body, you're going to lose it 2 ways. For example, I told you about carbon-14. I had to do an experiment in rats. And the FDA said, well, you're using this polyethylene glycol in this burn bandage. It's in contact with the extracellular fluid. And that means that some of that glycol is getting into the patient's extracellular fluid, which means it's getting into their body. And so we want to know where it's going before we'll approve your burn bandage. Okay, so I had to get some rats, had to figure out a uniform way to make a small burn. The rats were anesthetized. A small burn on the rat, and then use this little bandage on it with the polyethylene glycol. But I used the polyethylene glycol that was made with carbon-14. So now the rats were in a cage where we could measure. We didn't keep track of what they exhaled, but we kept track of their feces and their urine okay? We wanted to see where, you know, where the, this carbon-14 went. And fortunately for us, about 95% of it came out in the urine. So we were happy with that. So the FDA was happy with that. They said, but just to be sure, when you first put this on a patient, we want you to measure the amount of polyethylene glycol, not radioactive, but just polyethylene glycol in their urine, just to be sure. Because we had the model of the rat, the urinary model of the rat is similar to that of man. Anyway, so in the case of the rat, the half-life of carbon-14 by itself is about 5,500 years. So you're not going to see any loss in radioactivity. That sucker, okay, that's going to be around a long time. But the rat excreted it, you know, a lot faster. I wanted to point out to you, this is the biological half-life. So you have a physical half-life and a biological. And in order to get the combination of those, the effective half-life, you use the same equation that we saw with resistors, the last chapter, resistors in parallel, or we just saw with lenses, okay? Remember, the focal length equals the 1 over the focal length is 1 over the object distance from the lens plus 1 over the image distance from the lens. It's the same formula, the same structure. So, but since there's only 2 of these here, I just rearranged it like you guys saw in your book to get it directly so you don't have to deal with fractions. And it's just to multiply the 2 half-lives together and on the numerator and add them on the denominator. And that's equation in your book, equation 18.5. Anyway, so here's an example of that. Iodine-131 has a physical half-life of 8 days and a biological half-life of 138 days. In other words, it stays in your body a long time. All right? So, what is the effective half-life in your body? There it is, the effective half-life. You multiply the 2 together in the numerator and add them in the denominator, and then just crank it out. And it's going to be it's going to be pretty close to the 8. It's going to be closer to the smaller number. You're going to be getting rid of it pretty fast. Okay? And one of the problems you have in the book 1824, problem number 24, you're reducing 250, this is millicuries, down to 0.001 millicurie, and they want to know how long does it take to do that. And rather than give you a formula, I just worked it out the longhand way so you guys can see how many years it took. But it's, again, this is the same formula. You're starting with 250, right? Then after 1 half-life, you're down to 125. After another half-life, you're down to 63. Another half-life, 31, blah, 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 blah. We're all the way through that, just to show you how many steps it takes. It takes a long time for that. And I think that is it. That is it. All right. Please write to me, or if you're in the lab, we can talk about the problems in the lab. If not, please write to me with any questions about this.
So next week is that.
That's right. That's your last test. Right.
And then when do we present for our
The week after that.
The week after that.
Yes.
And then the week after that is final.
Yep. If you want to take it.
Okay. So will we do the final in class? We'll watch. Do you want us to watch the movie on our own, or are we doing the movie?
Oh, we'll do the movie, right, for the final? We'll do it. Is this room okay?
Yeah.
Your ass won't get too tired here?
No.
Right.
So you want us to, so we're going to watch the movie here, or you want us to watch it on our own?
No, watch it right here. There's already a handout to follow. Okay, follow it. You're going to like it. That's a good movie. Yes. Whatever you want. Don't want you to teach it, but it's something about areas.
Oh, that's right. Yeah, because I got an
For this class.